So let's tidy this up a little bit and maybe write it out. Let's see. Partial u bar with respect to time plus partial u bar squared with respect to x, partial u bar v bar with respect to y, plus 1 over t int of, let's see, partial of the quantity u prime squared with respect to x dt plus 1 over t int of the integral from 0 to t int of the u prime v prime product with respect to y dt. And then that all equals, on the right-hand side, our minus 1 over rho dp infinity dx plus kinematic viscosity times this second derivative of u bar with respect to y. Okay, so hopefully you can read. Sorry, this up here is u prime. Okay, so that's again the Reynolds average expression of the exponential momentum equation. So okay, where do we want to go with this? I guess what we want to do is figure out how we can rewrite this so that we can actually use it in models, like turbulence models. So this is kind of the first step that we get to. We have to maybe make a few further simplifications or assumptions. So let's see. Let me just sketch out a concept here, and then this will kind of help us make another assumption. So if we look at velocity as a function of time, and we look at, let's say, the u component of velocity and the v component of velocity. So u is going to look something like, let's use green here. So u is going to look something like this, right? V is going to look something like, v is, remember, the y component of velocity. So v is going to look something like this. So what do we notice, I guess, that the oscillations, because u and v are inversely correlated inside the eddies, the magnitude of oscillation or magnitude of velocity change in an oscillation is the same between u, this is v, this is v, this is u. It's the same, right? It's the same magnitude. However, the average velocity of u is much higher than the average velocity of v. All right, so we can use that concept to say that, let's write this out a little bit. So we'd say u prime is approximately equal to v prime. So we can make this observation that if I'm looking at how things change, right? If I'm looking at these derivatives of how things are changing, I can conclude that in the y direction, if I have a big velocity oscillation in the y direction, the length scale in the y direction is very small compared to the length scale in the x direction, right? So thinking back to the approximate models, if I'm looking at oscillation per height, that oscillation is much more important than the same oscillation magnitude per length, because length is so much bigger. Okay, so for that reason, we can actually throw away one of the gradients in the x direction. Okay, so if we do that, we're saying effectively through this simplification that our 1 over t int integral from 0 to t int of partial u prime, v prime, partial y dt, we're saying that that is much greater than the equivalent integral in x. So 1 over t int integral from 0 to t int of partial u prime squared partial x dt. So we're saying that's true just because of these, these observations. So with that, then we can further simplify the equation. Let's see. So doing that, I guess we would, let's see. So we'll just throw away this one here. That's what we just said. So this becomes our slightly more simplified equation, right? By one term, I guess. Okay, so now we're almost to a point where we can have things written in a way that's useful in a numerical model. Let's say you want to go plug this into a numerical model. I guess you look at this and you'd say, I've got these first order derivatives, and I want to have a model that just works on first order stuff. So you're kind of close here, but you have some of this second order things and integrals. So we need to maybe group some of that stuff together so we can come up with simplifying models for just those pieces. So if we take that next step, we would write this out as this following here. So it would be partial u bar with respect to t plus u bar partial u bar with respect to x plus v bar partial u bar with respect to y. Plus, now this is where we're going to try to start forcing it into a form that's useful. So we're introducing that continuity definition back into the equation again. So we say then u bar times our continuity, which is partial u bar partial x plus partial v bar partial y, right? That's 0, remember? So we're introducing that, and then we're saying then that's equal to minus 1 over rho dp infinity dx plus nu partial u, second derivative of u bar with respect to y, minus, and the last thing here, which is 1 over t int integral from 0 to t int of that partial u prime v prime partial y dt. So, okay, we've done just a little bit more manipulation, but this is a step closer to being useful. Again, it's hard to see where we're going with this, but what we're trying to do is, I've got these things. If I want to say take a numerical model and step forward, I want to be able to take a state equation and estimate how I should step in time. So I want to have first order derivatives from x position to x position, y position to y position, and so on. So you have these nice now first order things, except down here. Right? And that's where we're going to focus our effort on the turbulence model. So you can handle all the rest of this just numerically. Turbulence models end up focusing just on this stuff at the end. So, okay, let's make the last little simplification here. Actually, I think it's written out on the next slide, so let's just skip to that. So, okay, so the last step would be I took that thing I just wrote and then write out this. So it's exactly the same thing. So what we have then is our Reynolds averaged equations for conservation of, or continuity, conservation of momentum in the x. Again, conservation of momentum in the y is negligible because we're in a boundary layer. And then we could do exactly the same thing, which I won't subject you to, for energy, and you end up with this equation, right? But it's very similar. You just have temperatures instead of velocities, and you have here an energy transport due to turbulent eddies, which is a integral, this v prime times t prime, the temperature oscillations. It's sort of the same idea, but we have this nice model now that we can use to plug into our your numerical solvers, your finite volume solvers or whatever. So, okay, any questions on that stuff?
In the previous step, you added in continuity, but I don't see that in the summary.
Yeah. So where did that go? So what did we simplified to bring what? So the inertia part stays the same. We have the 0. Yeah, I think what I was meaning to say there was we can go from this equation to this equation algebraically. And then what I meant to say was that this, because this is still continuity, that equals 0. So that actually goes away. Right? Sorry, that was confusing. That goes away. So then we're left with this piece and those pieces there. OK. So normally, I guess you would start with this. Like you go look at this in the book and start with this. But it's really good to understand like where did this, like this is a completely new term. This wasn't in anything we've done previously. Where did this come from? Well, this came from making assumptions about what's important in an average model. What do we have to keep around in an average model? And it turns out you can't just say the fluctuations are unimportant, right? They are important, and they're important in the sense that they introduce transport in these turbulent eddies, and that shows up in this last term. So all the turbulent stuff effectively shows up like right here.